geWorkbench is a desktop application. The user interface has 5 sections. The one in the top left corner is the project folder, and this is where your data files are organized. To load an input data, you right-click on the workspace and click on New Project to create a folder to hold your input data files. And then you right-click on Project, then click on Open File. The test data we're going to use is B-cell 100. It contains gene expression data from 100 arrays, and it's a subset of 340 array from the original ARACNe paper. And the platform is Matrix U95. So we click on Open. Pop-up window showed up and ask you to load an annotation file so that the geWorkbench can translate the probe IDs into gene names. And it also tells you if you don't have an annotation file, you can download a copy from a Matrix website. You can continue. So the annotation file has to be in .csv format. Let's click Open. When the input file loading process complete, an icon and file name will show up in the project. If you hover the mouse over the name of the file, you will see the number of arrays and number of markers associated with this data set. And the complete list of markers will be displayed in the markers section under the project folder. So we mentioned in the introduction, the ARACNe is a component of a geWorkbench, but it is not loaded into geWorkbench by default. In order to use ARACNe, we have to make sure the ARACNe component is loaded. To do that, you click on Tools, click on Component Configuration. Now, this will be checked. You check ARACNe analysis, and then click on Apply. Then close the window. Click on the data set to bring up all the windows. If we click on the analysis, we'll see the ARACNe analysis is found in the list of analytical components of geWorkbench in the lower right corner of this functional window. Next, we're going to set parameters. First, the hop markers. The hop markers specify which gene markers will be treated as hops in the ARACNe mutual information calculation. The mutual information is calculated for each specified marker, hop marker, against all other markers. Submit the dataset. There are 3 options: all versus all, from sets, and from file. For simplicity, this demonstration will use 2 genes as hop markers, MYC and BCL6. We're going to set up a parameter to identify the genes that potentially forms interaction network with those 2 hop markers. To find hop marker, we type in the gene name in the search window and enter the marker. That's the BCL6. We find it's highlighted, and we double click. The selected gene will appear in the selection marker set in the bottom left panel. And we will do the same with MYC gene. MYC. There was more than 1 probes for this MYC gene. We will only select 1. So this is the one we're going to select. Double click. So you can see both markers are selected. We are going to use the set that we selected as a hop marker, the selection, and those are the 2 markers. The threshold type. So this drop-down box specifies the type of threshold to be used, and it can take the values mutual information or p-value. The actual value entered to the adjacent text area is always a number between 0 and 1. So we're going to use the p-value. We're going to use the same value that used in the original paper, 10 to the minus 11. There are 2 algorithms are offered with which to calculate the pairwise mutual information between markers. One is adaptive partition, and the other is a fixed bandwidth. We are going to use the adaptive partition. Again, please refer to the original paper or the geWorkbench main project site to find out more the reason behind which algorithm you use. Next is the mode. Used to control the calculation and the use of runtime parameters from the input dataset. It has 3 modes: complete, pre-processing, and discovery. The pre-processing calculates the required parameters and writes them to parameter files. It takes a long time to run. It only needs to run once for each dataset. Discovery mode calculates mutual information with this run and uses pre-calculated parameter files as needed if they are present. Complete mode combines both pre-processing and discovery. So since we already have the pre-processing run before, we just need to set up as a discovery. There is a DPI. As we mentioned in the introductions, data processing inequality analysis to remove indirect induction. For this illustration, we're not going to apply this analysis. So now all the parameters basic parameters that we need to run ARACNe set, just need to click on and analyze to run ARACNe. So the result of the ARACNe run is displayed in geWorkbench as a diagram of gene induction network. The diagram is displayed with another geWorkbench component, Cytoscape, which is a network and a pathway visualization tool. You can visit the geWorkbench main webpage to find out more about how to navigate a Cytoscape. There is a tutorial page dedicated to this topic. For us to get a better view, let's undock the viewer window. Here, the hop gene BCL6 and forms 2 centers of this induction network. The solid circles, triangles, and squares called nodes represent the identified genes or gene products. The lines that links between a pair of nodes called edges indicates the correlated gene pairs. As shown in the upper left panel, there were 350 genes and 403 correlations that has been identified through this ARACNe run. Some are genes correlated with BCL6, and some are genes correlated with MYC. And there's also some genes that are correlated with both MYC and BCL6. This video is intended to be a beginner's guide on how to set up and run ARACNe geWorkbench. If you're interested in learning more about ARACNe, please refer to the geWorkbench main webpage for more details. Thank you.